Okay. Confirm, can you hear me, David?
Yes, I can hear you.
Okay, thanks. So, well, if there's one message in the next 25 minutes that I'm going to try and deliver, and that it is that Inspire provides perhaps the best, or not perhaps, exactly the infrastructure that we need for applying the kind of artificial intelligence that David's just been talking about. It's unparalleled in the world for the kind of infrastructure surrounding semantics and standards for semantics and support for those standards. It's unparalleled. There are similar examples. Maybe one can think of EarthCube in the United States, but none of them is as expensive as Inspire. So these are the headings that I'll be talking under right now, but rather than stick with this summary, I'll just go straight to my slides. Oh, I should be on full screen. So some definitions first, which I won't spend time on, but they need to be up there. Artificial intelligence we view as the capability of a machine to imitate intelligent human behavior. Intelligence is the ability to learn or understand and apply knowledge. Knowledge is the fact or the condition of being aware of something and or its meaning. Meaning is what is expressed by a word, text, concept, or action. Semantics is the study of meaning. And language is a systematic means of communicating by the use of standardized signs, sounds, gestures, or words, having understood meanings. Can you see my screen?
Yes, we can see.
Yeah. Okay. My interface doesn't show the control interface anymore. Okay. So the conclusion is that AI needs language to communicate with human beings. Linguistics is the study of language, and there are a number of different levels of linguistics, starting right down at the sounds we make and going up to phonemes, words, phrases, and sentences, and then the literal meaning of phrases and what they may mean changes. In the context of this webinar, the three most important levels are obviously words, which correspond directly with the Inspire code lists. An example of a code list value is a granite. It's a certain kind of rock, and it's well defined by Inspire. Phrases and sentences, we now introduce really the concept of syntax, how these words relate to each other in structures like sentences, or as David spoke about, like triples. So we have a triple here, polygon 1336 has bedrock granite. That's a triple subject, predicate, object. And then obviously we're concerned about the meanings of those phrases. That this phrase up here means that the bedrock in the area of polygon 1335 has been determined, and it has been shown to be an igneous rock. The reason I put in igneous rock here is that because of the semantics defined by Inspire, we actually know that if something is a granite, it must be an igneous rock. So what we then need to deal with respect to the fact that an awful lot of the information we have at the moment in Inspire are in relational database tables attached to points, lines, or polygons. And yet I keep saying that in our field of AI, we work with triples, RDF, Resource Definition Framework, or semantic networks. There have been tools around for a long time that relatively easily convert tabular information to graph information. And we don't have time in this presentation to go into them, but they are there and they've been there for a while. So it's not a big problem converting from relational databases to semantic networks. At the same time, the syntax, a lot of the syntax and some of the semantics in Inspire are provided in the UML diagrams that lay out the relationships of different tables to geometric objects and so on. Turns out there are many tools out there for the conversion of or transformation of UML diagrams to ontologies. Again, we don't have time in this presentation to go into them, but here are a couple of academic presentations on the subject. A tool that we use quite often is provided by Top Quadrant as a commercial tool. So there are no great hindrances to converting relational database data and that's in Inspire and the knowledge frameworks that are in UML into ontologies. Returning now to our diagram of the different classes of artificial intelligence, we would just make the case that really the answer is not going to be only in semantic systems or only in machine learning systems. They integrate well together, particularly if one thinks of machine learning as often being considered really as a perception type of system, something that can do in seconds what human beings can do in seconds as well, such as facial recognition and extraction of patterns from airborne magnetic surveys. Whereas the cognitive side of things, cognitive systems take human beings a finite amount of time to think about and come up with answers. And very often in hybrid AI systems, we find the outputs from machine learning as providing very useful inputs to cognitive systems that we can reason about. So I think if you read the book I recommended earlier, the recommendation there is that hybrid systems are going to be the answer in the longer term for AI. What we also have to deal with in thinking about knowledge processing and intelligent systems is communication. And there are three kinds of communication we have to be concerned about. Communication between people first, and if we don't understand and get that right, we're not really going to get right communication between machines and between machines and people. So as this slide sets out to explain that many specialists in science at the moment are aware that as they specialize, they develop language that isolates them from their co-researchers. And we have this problem in mining, where metallurgists aren't speaking the same language as geologists, who are not speaking the same language as the environmentalists they have to work with. So, semantic solutions are the ones that are important here because they make explicit what we mean by our words, and they make them available to interdisciplinary groups to work with. Of course, it's not just human-to-human communication we have to worry about, it's machine-to-machine communication. And that was highlighted early in the 21st century by Tim Berners-Lee and his vision for the semantic web. Some people think this is a dated version of the world. I don't, and there are lots of people that don't. This diagram of the semantic stack, starting down here with Unicode and URIs, and eventually ending at the top in trust, has been rejigged by many people, but it still bears, it's still a very useful framework to design to today. His vision was of the semantic web of machines being able to talk to each other, which depended, of course, on defining the words with taxonomies and ontologies. Now, when we get onto the vexed subject of how we can communicate with computers, it highlights the fact that we're very inconsistent in the way that we communicate with ourselves. But human brains can take that into account in real time pretty easily by just saying, can you repeat that, or tell me what you mean by that word, and so on. Machines can't do that, so we have to be very explicit with machines about the words we use. The challenge is sort of well represented by the fact that in my period of 30 or 40 years as a geologist, I've had to work with at least 5 different taxonomies of rocks, and it was grappling with these different taxonomies over a period of 3 or 4 years that the group behind the One Geology site that Matt may mention later today grappled with this to come up with a single sort of overarching taxonomy of rocks, which has now found a home in Inspire. And I think there are many different taxonomies that Inspire uses that need the discipline that was attached to coming up with one coherent Aristotelian, we'll talk about that just now, taxonomy for rocks. And this discipline needs to be applied to all the taxonomies that are in Inspire. So really the concept we're talking about, or in the vision for Inspire as a framework for artificial intelligence, is that we can use the words, the actual code words that are in the code, the words that are in the code lists of Inspire to do the computing upon. We reason with the very words that are in the data columns of your objects in the maps. And this slide is just trying to represent how that works. If polygon has slope very steep, has road cutting, yes, has current rainfall very heavy, then current rockfall hazard is very high. That is it's a piece of reasoning that can be done with the content inside the data columns of your current maps, but it can only be done if the semantics are absolutely correctly defined. David's already described what an ontology is. This just presents a graphic that makes it a little clearer. Ontology editors are quite complex beasts. They have the taxonomy, they show the taxonomies to the knowledge engineer, a little bit of metadata about the taxonomies, and importantly, the definitions for the words. And it's from these systems that the user interfaces with the domain experts or with the relational database to RDF transformation software. It's by referencing through these kind of systems that we can move our data into semantic networks like this, this description of a mine. Now, ontologies are built from term lists, and those term lists, many of them are either taxonomies or partonomies. And this is an absolutely fundamental concept to be understood if one's going to be using taxonomies for reasoning. And it's a concept that's not often explained, because these two kinds of hierarchies are often conflated. And so dealing first with the kind of hierarchical relationship on the left, this is called a taxonomy in its strictest definition, and it was first recognized as an important data structure by Aristotle many years ago. And here we have an extract from the rock taxonomy in Inspire at the moment, which says that a volcanic rock is a kind of igneous rock, and a rhyolite is a kind of acid rock, which is a kind of volcanic rock. This is very different from a partonomy, which is also may also be hierarchical, and is explaining what a rock is in terms of its component. So this rock has a mineral, and the mineral has an element. So the element is part of the mineral, and the mineral is part of the rock. And in reasoning systems, it's important to know that some of the properties of, in a kind of relationship, propagate up the hierarchy. So if the mineral has element mercury, then the rock has element mercury. So this attribute has propagated up the hierarchy here, in exactly the opposite direction from which properties propagate within taxonomies. Within taxonomies, they propagate down the hierarchy. So anything we say about anything that is true about a parent class of a gabbro or of a granite is true about the granite. So properties propagate down this hierarchy. If these two are mixed, if they're not distinguished in a code list, you cannot use that code list for intelligent reasoning. This subject is explained in more detail in a book co-authored by David and Professor Alan Mackworth on artificial intelligence, and that book is available free online, and this concept is explained at this reference. This is a slide to highlight the unfortunate fact that one of the most popular, globally most popular terminology editors is called SKOS, Simple Knowledge Organization System. And it's really grown out of library science, where the people needed to know where to put their books to most easily make them found. And the relationship in a SCOS hierarchy, I will not call it a taxonomy, is broader than and narrower than. And if you think about it, that explains why there's this conflation of kind of and part of. It doesn't distinguish between the two, so you end up with kinds of and part of relationships all mixed up. This diagram on the left illustrates how the enhancement of molybdenum, this is a semantic network describing a mineral deposit, and if we found out that a particular mineral assemblage has enhanced molybdenum in it, this has implications for the zone that it's in, for the host, the rock that hosts that zone, and indeed for the deposit. This has an awful lot of relevance when one is searching through information like this, because if we've entered molybdenum here and not entered it here, and someone's looking for a deposit that has molybdenum, their software either has to search through the semantic network, or during knowledge capture, this attribute needs to have been propagated onto all the nodes where it actually belongs. So that's what we're trying to show there. Getting back to the semantic network, I beg your pardon, the semantic stack, it turns out that pretty much each of the components of the semantic stack, as Tim Berners-Lee envisaged it, merits in a cognitive AI system a different piece of software. We found this in Minerva, and so, you know, at the very bottom end, when we're introducing relational databases to RDF format, we have software called DB Converter, brings it in, filtered through an ontology. We need an ontology editor. These are complex things to write, and we use a commercial one called Top Braid. We'll talk about the alternatives later. We use a specialized taxonomy editor that respects the Aristotelian principles for creating our taxonomies. We have our own proprietary reasoner, which can prove that our answers put out by the system are correct. And we have a document management system that is able to use the controlled vocabularies of Inspire to make it easier to search through our documents, and also to use those documents for knowledge entry into the system. So trying to close the gap, if you like, between knowledge expressed on the computer and knowledge expressed in the scientific literature. So let me just check where I am on my time now, 7:43. Yes. Okay, so now a little bit about Inspire semantics themselves. Probably most of the people on the workshop know that Inspire standards cover 34 themes of broad societal importance. This is a very broad scale of standardization of terminology and knowledge models in the UML diagrams. It's unprecedented in scope in the world, I would say. And another way that it's unprecedented is that it's legislated. So I know there are problems in respect of uptake, but let's hope that those problems are overcome, because there is no other way out to build intelligent systems other than standardized language to some extent, and provide the tools to for people to evolve those standards and to add to them in a convenient way. And Inspire provides all of those. So go on to the next slide. When I say unprecedented, it is nice to think of other examples in the world where government has stepped in and said they want to get involved in semantics. And to some extent, the Canadian government, interestingly, did this about 25 years ago as the result of one of the world's biggest frauds. Some people on the seminar may remember the Bre-X fraud, where claims by this company to the mining industry and the investing general public were that they'd found the biggest gold mine in history in the world, and it was all a big scam. And in order to preserve the status of the mining investment industry in Canada, the Parliament of Canada introduced legislation governing how geologists like myself will write technical reports about newly discovered mineral deposits. That is the National Instrument 43101. You can read about it. they don't actually define the very terms we have to use in the different paragraphs, but that national instrument lays out 24 or 25 different headings that we have to write about when describing a mineral deposit and its economic viability. And I wonder how long it's going to take before certain governments promulgate similar legislation compelling their scientists, when writing up environmental findings and so on, to use a language that is understandable to the computer so that the computer can aid the kind of e-science and hypothesis testing that David spoke about earlier. If one scientist is writing up with one set of terminology and another scientist is using another, it's impossible to do the kind of work that David spoke about earlier. So this diagram is simply an illustration for those who don't work closely with these standards in Inspire, how the UML diagram is providing an awful lot of knowledge structure, both in terms of syntax and semantics. This is the high-level geology UML diagram for how geology is implemented in Inspire. And what we see it being explicit about in this part of the diagram is a part of relationship, compositional part of a geological unit. And in this part of the UML diagram, it's being explicit about a kind of relationship, how natural geomorphic features can be parts of geomorphic features, but you can also have anthropogenic geomorphic features as part of a geomorphic feature. It's interesting to note that we're not the only people that have been playing around in this area of converting UML diagrams into ontology and the technology of the semantic web. There are clearly a number of people in Inspire who over the last 5 or 6 years have been publishing on addressing exactly the same challenge. Okay, so drilling down now to some of the more nitty-gritty detail. How does Inspire, how are these semantics presented to the users inside of Inspire? I thought it appropriate just to show that the Inspire website has fairly good navigational system for hunting around the different themes that it addresses and the many different taxonomies and mixed up partonomies that these formalize. And here's just an example of the semantic detail that is in them. Very clear definitions in English and the other languages of the European Union for each of the codes in the code list. So here, Earth surface setting is defined in clear English. So as I've been intimating, some of these code lists have been prepared by people who were aware of this distinction between part of and kind of, and some were not. Fortunately for us working with a lot of the earth science, using a lot of the geological taxonomies in our reasoning, the groups that worked on the GeoSciML standard and in the One Geology environment were aware of this, and we can pretty well use the taxonomies or the code lists in most of the geology specifications as is. This Aristotelian class explorer, the ACE taxonomy editor that Minerva provides from its website as a free-to-use tool, is able to import all of the code lists in Inspire, whether or not they are true Aristotelian taxonomies. And once within the ACE system, and this is the purpose of ACE, one is then in a very strong position to sanitize them, if you like, to re-engineer them and to extract from them, take out from them the part of semantics and put them somewhere else and make them true Aristotelian taxonomies that can be used in reasoning. And here is an example of a common one that there's a fair bit of literature about people struggling to get right, the Hilux land use classification system. It is one of the standards in Inspire. This is an elegant hierarchical diagram that Jake McGregor produced in his workshop on how to use ACE, presented yesterday. And what he was pointing out, and what I'm pointing out as well here, is that there is a conflation here of kind of relationships with part of relationships. Farming infrastructure is not a kind of agriculture in the same way as agricultural production for own consumption or agricultural production for commercial production is. And if you want to know more about the difficulty of mixing up these relationships, have a look at the recording of Jake's webinar yesterday when it comes out at the end of the virtual Dubrovnik workshop. In the background here, I show some of the workings that some of our staff have engaged in trying to sift out the part of and kind of relationships actually in Hilux. So this is a printout in Excel of the hierarchical arrangement of the Hilux terms with their definitions. And in this case, the knowledge engineer is trying to work out what the subject, predicate, and object is in the sentences describing the term here, so that we can clearly understand which is part of and which is kind of. If one thinks into the future about how AI is going to be important, one of the most important areas is going to be how it combines the law and what we as scientists or environmentalists are seeing in the environment and in our surroundings, especially in the time of climate change. So we can imagine that the link between the science that we represent in our maps and the law, in particular European Union law, is going to be important. And we can envisage a time when our data, just like David explained earlier, once it's in standard terminology, if that terminology is the same as the terminology in the law, then we'll be able to much more easily see where the law is being complied with and when it's not being complied with. Turns out that in the European Union, significant advances have already been made in interfacing case law with ontologies and with carefully selected taxonomies and word lists. And I draw attention to this European Commission finance study over the years 2013 to 15. The study was called EU Cases and has led to the commercially viable product. You can now go to the Euro Cases, closely named, not EU Cases. Now it's called Euro Cases. It's a commercially viable product offered on the internet as a software as a service. It's a unique multilingual information service providing online access to case law of the leading jurisdictions in Europe related to the application of European law. It's all built on a semantic back end, relying on thesauri and taxonomies. And this, in my view, is an environment, again, that's unparalleled in the world, and all provided by Inspire and Inspire type tools and technology. So if we think of Inspire as an ecosystem for managing semantics, what does it offer? Well, these are just for those that are not familiar with them, these are the areas that it offers entry to the system from the home page. There are learning headings, there are implementation headings, there are participation headings, and guides for users. These facilities and services are all necessary for large-scale deployment of cognitive AI, and we don't see them being deployed quite like this anywhere else in the world. So examples of, just checking my time here, 7:55, I'm okay. Aspects of what Inspire provides with respect to maintaining semantics are first a theme community management. So there is a place to go if you need to ask a question or air your grievance about certain semantics that are important to you and that are in the standard. And, you know, there are other groups in the world that have this on more focused groups, and how these groups can interact with those focus groups is a challenge for the future. But you've got to start somewhere, and this is the most integrated, broadest based community management theme area that we're aware of globally. Importantly, each of these theme areas has a nominated person, a human being that's in charge of moderating and curating the semantics that have to do with that theme. And if you hunt around the Inspire website, you'll find that some of the themes are actively seeing contributions, and certainly in one or two of the themes we're interested in, the ones to do with natural hazards like landslides, the discussion groups are reasonably active, and they're certainly talking about important things as evidenced here. Now, critically important to any standard is, for its adoption, there must be some flexibility to allow the users of that standard to adjust it in one way or another, so that if they have an application that really needs some other semantics, they are not crippled if they don't include the semantics that they need. And incredibly wisely, Inspire provides that facility by allowing for extensions to their standards and a very solid infrastructure for making any extensions that you make evident to other people so that other people can use them. And this provides an evolutionary path for standards to evolve and get better at their core with the passing of time. And there's no doubt that that's going to happen. So anyone who's really interested in AI of the future needs to be interested in how you evolve standards, because language itself moves. Human language moves. So on the Inspire website, the software that actually runs their registry for registering all the code lists and the theme standards is called Registry, but it has a 3 in front of it, RE3, GISTRY. And this is a software system, a web software system that can be set up independently by users who want to be compliant with the Inspire standards on their own servers. And so long as they follow the guidelines provided by Inspire, they can extend the standards in Inspire, serve them in their own registry, and thereby be Inspire compliant. And as you'll hear from Gio later today, Minerva has chosen to do this. In the detail with which we address landslide hazards required more detail than is available in Inspire. And we set up our own Inspire registry. We've followed all their guidelines. Our application is therefore Inspire compliant, and all our terminology and syntax and semantics are available for other people to use. So with respect to the tools available for working with these semantics, it's clear as well that other people in the European Commission were interested in ontologies, because they have funded over time an ontology editor called VocBench, which is now available in its 3rd edition. I'm not sure how many users there are of VocBench in the world, but I felt it important to draw this tool to the attention of the seminar. There are a number of other tools to choose from, such as the open source Protege ontology editor that comes out of Stanford University. Has a bit of a learning curve to it, as does the one we use, which is a commercial ontology editor called Edge. Edge stands for Enterprise Data Governance. It's put out by Top Quadrant. There are many choices that one can make for editing one's own ontologies. And in this environment, I need to come back and emphasize that if you're interested in code lists that can be used in AI reasoning applications, then please take a look at the Aristotelian class editor. There's a fair bit of up-to-date documentation around it on our website and within the Poole and Mackworth text on artificial intelligence. So now just a few words on I've spoken about AI and semantics, and I've spoken about the semantics within Inspire. Just a few words before I hand over to Gio about Inspire and AI. I think there are at least 3 facts that we can bear in mind now. Standards are required for interoperable data and knowledge. And this interoperability is important at both scientific, legal, and social levels of our society. At the same time, interoperable data and knowledge are required to build scalable AI applications. And the semantics of data used in AI need to be made clear for AI output to be explainable. So if we have a vision, and this in many ways has been the vision of the company Minerva, ironically, we're not a European Union-based company, but because of all this vision for Inspire, we have established an office in Darmstadt, where we work fairly closely with one of our partners, We Transform, which is also a company that's committed to the future of Inspire. If one believes in these facts, then the vision is that we should leverage the considerable Inspire standards infrastructure to provide the globally scalable AI applications of the future. That's the vision of Inspire and AI. How do we implement AI applications based on Inspire? Well, we need to identify problems that need solving and identify tools and a team structure to solve them. So first, what are some problems that need solving? And David's touched on 2 of them that we've addressed over the last few years. Where are the mineral deposits? We've built an online AI system which explains its reasoning that's available for everyone to test and use on our website. It's called Yukon Mineral Targets, and it addresses mineral targeting in the Yukon in northern Canada. We've also built one that Gio's about to show you, which addresses a problem of deciding where are landslides most likely to occur in the Veneto area of Italy. So these are examples of problems that can be solved, that can rely very heavily on Inspire infrastructure and demonstrate to the people who want you to believe in Inspire that there are rewards for those who adopt Inspire standards. There are carrots, not just sticks. A key part of being able to deliver on this vision is identifying the tools and a team structure to solve them. And it needs to be emphasized, I think, that to solve these problems, it's not enough only to have a domain expert. It's actually important to have a knowledge engineer, what we call a knowledge engineer as well. Doesn't have to be a Minerva one, but it's got to be someone who's technically at least interested in semantics. They don't have to have a university semantics training, but they need to be aware of the difference between kind of and part of. They need to know how to use a simplified ontology editor like ACE, and in the best case, they may need to know about how to use Protégé or Edge. We believe that without this kind of team at the core of these applications, they won't be built successfully. And then, of course, they need to surround themselves with the kind of tools that we've developed for ourselves. There are other tools like this out there. In the case of intelligent document storage, we've built something called LEO, which stands for Language Extender and Organizer. But we're aware of others that are out there that are more domain specific than ours. There's one called Climate Tagger, which is developed by a semantic web company with Pool Party for assisting scientists in the climate change area. And then there's one developed by the OBO community called Ocean Best Practices, which deals with the taxonomies and all the terminology for oceanography. So these are the tools that teams like this need to have to deliver actionable results with explanations in truly AI type scenarios. Once you've got those, then you've got to obviously populate the team with people. You have to establish the semantics of the problem, use the Inspire models and code lists where possible, create and register extensions where they are needed, and engage with the theme curators regarding possible revision of data knowledge models and code lists, and then deliver the results. And that's what we're going to see an example of right now. And I think I'm exactly on time. I'm 5 minutes ahead. Yeah, with that, I'd like to hand over to Gio Roberti to tell us about Inspire frameworks for landslide hazards. Thank you.